In the fundamental course, we have studied many different sorting algorithms with the assumption that everything is done in the main memory, right? And that our main memory is large enough to hold all the data. External sorting is about sorting big data. So the data set is so big that it cannot be loaded completely into our main memory. And the data set is stored on a disk or say several disks. Alright, so the first natural question is, why can't we simply do quicksort on a disk? Why not? The key difference is on the random access, that is, to get A of I for any I. If it is done in internal memory, it will be very fast and the time can be considered as a constant. But if it is on a hard disk, we're going to have to spin the disk to first find the track and then find the sector and finally find this element A of I and transmit. And it's not only very slow but also device dependent. So what we would prefer to do is to store the data sequentially, put them all together so they're not too far away, and keep the head moving in one direction as much as we can to avoid spinning the disk very often. Alright? So now, when we think about all the sorting methods we have learned, which one is the best for this task? Merge sort, right? Well, the instructor of the fundamental course must have mentioned that since merge sort takes a linear extra space, it's almost never used in internal sorting, even though it has a pretty good complexity, which is n log n, right? But it's a very powerful tool in external sorting. And the key step in merge sort is merging, right? So we may have 3 disks, and so 3 heads pointing to the elements, and each head only need to move 1 unit at a time in one direction. And that's why it's so good. Alright, so we're going to talk about how to use merge sort to do external sorting. And to simplify, we assume that all the data are stored on tapes. So it's a linear tape that can only be accessed sequentially. And we assume that we can use at least 3 tape drives. And there's a reason behind, and we're going to see. Let's start with this example. Say, suppose that the internal memory can handle only 3 records at a time, and we have that many numbers on the tape. And this is our internal memory. Okay, so what we do is first we will load those numbers from the tape to the internal memory one by one and sort them using any algorithm like quicksort or whatever. So to sort them and obtain so-called a run. Okay, a run is defined to be a sorted sublist. So after obtaining a run, we will then write this run to another tape. So this is where we write the first run. And then for the second run, we cannot write the second run onto the same tape. Otherwise, we won't able to merge them. All right? And therefore, in order to execute merge, we need another tape for the second run. So let's sort the second run and write them onto the third tape. And the next run, and the next run, and finally this run with only one number. Alright, now we have 2 tapes. Each contains several sorted runs. Now we are ready to merge them. And we should merge them to where? Well, after the first pass, we generate those sorted runs, and tape 1 is now available. Alright, let's merge the first 2 runs. onto the first tape, and then to merge the second two runs into where? We cannot merge them onto tape 1, alright? And that's why we need yet another tape, the fourth one, to store the results of this merging. Okay, finally, merge 15 with nothing, so we copy 15 onto the first tape and do another merge. Now tape 2 and tape 3 are both available now, and therefore we can merge the results back to tape 2 and tape 3. So what do we get? We get the result of this one merging onto tape 2 and the result of this one merging onto tape 3, and finally merge back to tape 1 and obtain the final result. So the number of passes is what? Is 1 for generating those runs plus 3 mergings, right? So the number of passes will be 1 plus 3. In general, if we have n records and the size of internal memory is m, then what is the number of passes? Now let's try this one. Say we have 10 million records of 128 bytes each. And the size of the internal memory is 4 megabytes. Then how many passes we have to do? To answer this, we have to calculate the number of runs first, right? It will be altogether 128 times 10 megabytes over 4 megabytes. So there are going to be 320 runs, right? So the number of passes will be 1 for the first run generation plus what? Plus log of 320, right? Which is 9. So altogether, we're going to need 10 passes to sort them. So in general, it will be 1 plus log of n over m with base 2. So in general, when we have to do external sorting, these are the points that we concern. First, the seek time. That is, when we merge, the head is moved step by step from the beginning to the end. And then we're going to have to rewind the tape and move the head to the beginning again. And that time is the seek time. So the seek time is basically related to the number of passes. All right. And we're also concerned with the time to read or write one block of records, the time to internally sort m records, and time to merge n records from input buffers to the output buffer. Here, the good news is that the computer can carry out input, output, and CPU processing in parallel. So in order to make some improvements, people have worked in the following directions. One is to reduce the number of passes, and then to speed up run merging, and carefully design the buffers so it's convenient for parallel operation. And finally, the run generation. And then we're going to take some time to discuss each of these 4 targets.